Hi everyone, I'm Masoud Agassi, and in this video series we are going to learn about processes and threads. Whether you are new to this topic or want to understand it better, this series will explain everything in a simple and practical way. Let's get started. In the last 4 parts we learned about the definitions of processes and threads in the context of an operating system, process scheduling policies and the steps involved in a context switch, and the most important challenges of concurrent programming that every software developer should be aware of. In this part, we will explore some of the best practices for utilizing threads in Java. In concurrent applications, we often need to execute multiple independent units of work called tasks concurrently. This use case is so common that Java provides an abstraction layer and implementations for it known as the executor framework. Let's review this framework with an example. In this program, our goal is to find the count of all prime numbers within a given integer range. How can we implement concurrency for this program? At first, we might think to simply create a new thread to check each number in the range. Let's review the code for this implementation. We declare an atomic integer as the counter. Then we define the start and end of the range to search for prime numbers. Inside the main method, we loop over all the numbers in the range. For each number, we create a new thread and pass a runnable to it. Inside the runnable, we check if the number is prime and increment the counter if it is. However, there is a big issue with this implementation. As we saw in the previous part, threads have memory and operational overhead. For processor-bound programs, it doesn't make sense to create more threads than the number of available logical processor cores. For example, if our system has only 12 logical cores, we should ideally have a pool of 12 threads to perform the prime checks concurrently. This use case is so common that Java has already implemented it as part of the executor framework. Instead of developing and managing our own thread pool, let's update this program to use the executor framework. First, we need to create an instance of executor service. In simple terms, executor service is an object that executes submitted tasks. It represents an asynchronous task execution service and decouples task submission from task execution. Using the executor's utility class, Java provides many factory methods for creating various types of executor service instances. For example, new single thread executor creates an executor that uses a single worker thread. New cache thread pool creates a thread pool that creates new threads as needed but reuses previously constructed threads when they are available. New fixed thread pool creates a pool with a fixed number of threads which are reused to execute multiple tasks concurrently. This is exactly what we need for our use case. Now we only need to pass the runnable tasks to the executor service, and we don't need to create and manage threads ourselves. After submitting the tasks, we call the shutdown method on the executor service. This allows previously submitted tasks to execute but prevents new tasks from being accepted. Then by calling the await termination method, we wait for the existing tasks to finish or for a timeout to occur. And if a timeout occurs, we forcefully shut down the executor service. This solution works perfectly for this problem. Now let's consider another use case where we need to return values from tasks. Runnable is an interface for tasks that don't return any values. However, there is another task interface called callable, which allows tasks to return values. Let's update our code to use callable. To receive the result of a callable, we need another class called future. A future represents the result of an asynchronous computation. It provides methods to check if the computation is complete, wait for the computation to complete, and retrieve the result. For example, after submitting the callable and receiving the future, we can call the get method on the future to wait for the computation if necessary and retrieve the result. The get method will also throw any exceptions that occurred during the execution of the task. There are many other types of executors and additional methods provided by the future class to help with executing and managing concurrent tasks. While we don't have time to explore each of them in this video, I recommend checking the Java documentation for the executor framework to familiarize yourself with all its features. You may encounter other concurrent programming use cases that require more complex task management. For example, chaining tasks sequentially, combining tasks and waiting for all of them to complete, or applying the same error handling logic across multiple tasks. To support these advanced asynchronous programming use cases, Java 8 introduced completable future. Let's see how we can leverage completable future to tackle these kinds of use cases by exploring another example. Suppose we want to write a program to fetch the list of all users from a database, fetch the list of all products from a database, fetch the list of categories for the retrieved products, and finally print a JSON string consisting of the retrieved users, products, and categories. Let's assume we already have classes for users, products, and categories, as well as blocking methods to fetch data from the database. To achieve this, we need two concurrent tasks to fetch the list of all users and products. Once the product list is fetched, another task to fetch the list of categories for those products. After all data is retrieved, a final task to generate and print the resulting JSON string. An exception handling to catch and print any errors that occur during task execution. Let's implement this using completable future. First, we will create a completable future to fetch the list of all users. The supply async method of completable future takes a task to execute asynchronously and returns a completable future for that task. Similarly, we will create another completable future to fetch the list of all products. Next, we need to run a task that fetches the list of categories for the retrieved products immediately after the product list is fetched. We can implement this using the then_apply_async method. Now we will combine both completable future instances into a new completable future. When this new completable future completes, we will prepare and print the resulting JSON string. We will also handle any exceptions that occur during the execution of these tasks. Finally, we will wait for all tasks to complete using the join method. Here we have used many of the completable future methods, so let's briefly explain how some of these methods behave. The supply async method is the starting point for asynchronous execution of a task. The task begins executing immediately when supply async is called. and by default, the task runs in the common fork join pool or a custom executor if provided. The then apply async method executes asynchronously when the previous stage completes, and always runs in a different thread from the common fork join pool or a custom executor if provided. The then run method executes immediately when the previous stage completes. If the previous stage is already complete when the method is called, the task runs immediately in the current thread. But if the previous stage is incomplete, the task is queued and runs in the same thread that completes the previous stage. The exceptionally method handles exceptions that occur during the execution of a completable future chain. And finally, the join method is a blocking call that waits for the entire completable future chain to complete. Before closing this video, let's briefly review the usage of parallel streams in Java. The Stream API was introduced in Java 8 and provides a way to process collections of objects. While the entire Stream API is beyond the scope of this tutorial, let's explore how to use parallel streams to write a concurrent program. The goal of this program is the same as the one we developed using the executor framework, but this time we will implement it using parallel streams. Inside the main method, we generate an integer stream for the target range, convert it to a parallel stream, map each integer to a Boolean value indicating whether it's a prime number, filter the results to keep only true values, and count and return the number of true values, which represents the count of prime numbers in the target range. Behind the scenes, the parallel stream splits the data and uses the common fork join pool to perform calculations concurrently. While parallel streams abstract away the complexity of thread management, they are best suited for processor-bound tasks and large datasets where the overhead of parallelism is justified. Thanks for watching part 5 of this tutorial series. In this part, we explored some of the best practices for using threads in Java. In the next part, we will learn about best practices for addressing concurrent programming challenges in Java. If you found this video helpful, don't forget to give it a thumbs up and subscribe to the channel for more tutorials like this. It's going to be an exciting journey, so make sure to stay tuned.